Alrighty. Well, welcome. This is round 2 after like a number of months of, releasing the first Casper video a while ago, and there's been a number of changes. This presentation should have like a similar format as last time, and that means like please ask all the questions possible, because that was kind of why the other presentation was cool. And now I actually have a bunch of proof of stake experts on the call, so if I sound stupid, everyone can chime in. So this is super exciting. So I know the people here really need some blockchain basics. I promise this will be super duper quick. So, right, we have our little blockchain, we have all the transactions, Alice sending 5 ETH to Bob, and Bob sending Dan and GNT and submitting a vote, all these things. And the kind of state of the blockchain is just all of those blocks with all the transactions kind of combined, the result of that execution, right? And so the current state of the blockchain, result of executing all blocks in their transactions. Super simple, but like if that's some core information that is important for this kind of stuff. So first, starting with proof of work. The way that the hybrid Casper is going to work is we're starting out, we're keeping proof of work as the block proposal mechanism, which means that it's a kind of should be a smoother roadmap. But first, let's like understand how proof of work works, because everyone who knows what that is. So basically, miners receive transactions and they burn some energy and can create a block if they burn enough energy, right? Like they compute the hashes and they receive a reward, right? So, okay, that's pretty cool. And, more transactions, more blocks getting mined. Once again, right, the current state of Ethereum, which Ethereum, by the way, of course, uses proof of work right now, and we're moving to proof of stake, is the sum total of all those transactions, right? And so a new miner arrives and we can have things like a fork. Now, the cool thing about this is that we now have like two sets of history, where one set of history where this miner, got the reward, the other where this miner got the reward. And so this miner just so happens to be, it's like a bigger character, so it's clearly a better ASIC farm. And
real quick question about forks and slashing conditions.
okay.
Basically the finality part. So what happens to the money that gets slashed? Does that get redistributed to the rest of the validator set, or does that get burnt?
Yeah, that gets burned. And I'll go into depth on the kind of like slashing conditions and the burning pretty shortly. Cool. So basically we have this like cool incentive where because this block was not included in the history, and that block reward is not going to the miner, there is this incentive to actually mine, for this miner to switch over and mine on the longest chain, right? So this is like, okay, cool, proof of work works. And it's like a super duper, it's super simple and elegant algorithm. And I definitely am a big fan of proof of work, right? And yeah, great. So, mining on shorter forks doesn't provide the block rewards. And so we have this incentive to mine on the longest chain. So, continues here. And the darker it gets, right, it shows that it's like harder and harder to revert. And so there's our chain. Great. But not so fast. Proof of work isn't perfect. That's why we're here. Well, there are a number of issues that are kind of that we see with proof of work, which is, one, clearly like wasted energy, and that cannot be stated enough. Two, it's vulnerable to ASIC centralization and other things that I will talk about later. And it also lacks finality. And this is kind of like a key point, this finality stuff. This is very exciting. So first, of course, Ethereum proof of work already burns more energy than small nation states. And I think we can do a lot better than that, right? Like we can certainly create a protocol which is as cost effective as possible. And being cost effective means that we actually, as users on the network, don't have to pay the miners so much, right? Because the miners are going to be like burning all this energy. That means that we have to overpay them, right? We have to pay for all this stuff. It's really coming back to the users of the system. So if we want a blockchain that is cheap and safe, proof of work I don't think is really the way to go. Another issue is ASIC or miner centralization. You can do chain reversions. You can also do a lot of other funky stuff, and the kind of cost of capital of creating an locating your miner near energy. All of these things are kind of like centralizing forces. And of course, this is macroeconomics. So if you're a proof of work fan, I have sympathy for you saying that my macroeconomics is not your macroeconomics. So right there's this miner, this gold miner has some crazy ASIC, and just starts mining up a storm. Oh my god, what's happening? Boom, blockchain reversion. All this history goodbye. It's very sad. This is not good, right? And so things that we want are like a in protocol penalty for reversion rate, some kind of like thing that will kind of discourage this behavior. Maybe outside of there is of course a penalty for mining on this chain because you have to expend a lot of work, but it's not an in protocol thing. This is an extrinsic resource. It's also difficult to recover from 51% attacks. People say that you can like mine at a loss, and that but I think it's less compelling than a hard fork away the coins. And also it doesn't have finality, clearly, right? Because we just reverted all these blocks. So blockchain is reverted. This is not a good thing. You can let's say you wanted to withdraw from your exchange right here, and then it updates your balance on the exchange, but then there's this big blockchain reversion, and what are you going to do? Now you have no money on the centralized exchange, and you have no money in your actual wallet because there was this reversion. So not good. And this is real, right? Like UAS F was like really scary because it could revert huge number of blocks, right? Like that's these attacks are definitely theoretical because they're just so massive in terms of scale. But the fact that we've already seen kind of the effects of having this like potential reversion is, I think definitely compelling to me. Boom. So that's our kind of like review of proof of work and explaining why finality is so important. Any questions? Feel free to ask.
Okay.
Oh, we have a little bit of a conversation going in the group chat. I don't know if you saw. There was a couple questions.
Oh, I didn't. Oh, whoops. What's up? What are the questions?
Well, I have one. It's not in the chat, but does this happen? Like, have we ever seen a 100 block reorg in Ethereum? Are we solving an existing problem in that sense?
Yeah, I definitely have not seen like crazy attacks on the protocol, and we haven't seen crazy attacks on a lot of these protocols. I think we're pretty lucky in that because the industry is like so nascent, we have a lot of really insecure blockchains that could just be like 51% attacked or messed up in a bunch of different ways that it just hasn't been done because people are probably like doing other things with their lives. But the most real kind of real world example of this would probably be like the threat of the UAS F reversion. That's like that is like in terms of like a long range reversion, I would say that's probably the most real.
But wouldn't you have that threat on FFG also? Like, couldn't I just say I'm going to start ignoring all the validators who don't mind SegWit blocks, and then change the signature algorithm for the other SegWit validators, so that they can't be slashed on any other old chain or alternate history, and then sort of launch the same thing?
Say that one more time.
So like the way I see UAS F
Yeah.
is that it's sort of indistinguishable from a hard fork in terms of real world network effects.
Yes.
So can I just hard fork FFG and change the rules and the signature format so you can't bring my conflicting transactions to the old chain and penalize me?
So I would say that would you agree that in like within the context of the UASF thingy, the old chain, right, would have had to would have had to hard fork if they wanted to, you know, be sure that the like soft fork chain would never get so heavy that it takes over their like main chain, right? So like
it depends on like what the miners choose, right? Like if 99% of them keep mining the non-UASF chain, then the UASF chain probably would have had to hard fork in a difficulty fix or something, or a new POW algorithm probably. But yeah, if the majority of users and the economy supports the UASF, then yeah, sure, the minority would need to change the rules somehow.
Yeah, or what I'm saying is like the majority chain was in a constant threat of this minority chain, because the minority chain would be able to, if the minority chain did actually get to be like a longer chain, then at least without some kind of special fork choice rule, all the miners would switch to that minority chain, or, you know, what was once considered the minority chain, that now, which only has, you know, the SegWit blocks. And
yeah, but that risk I sort of see as analogous to like all the validators leaving a fork they don't like they just stop participating on it.
I don't see that quite as analogous, because we don't have this risk of reversion in the same way, right? Like we know that if there's a group of validators that are validating a checkpoint and they, you know, that checkpoint is finalized, then there is a guarantee that that checkpoint is not going to be reverted, right? There, and that even if the validators stopped validating on that fork, it would not, it wouldn't actually change the fact that, you know, that you know, block is in the quote unquote main chain of that fork.
I don't want to derail it too much, but I think you could do the same thing for a proof of work fork. You can just like say this is a checkpoint.
Yeah.
I'm gonna
you totally can.
In my client, and then we'll all be, you know, kumbaya.
Absolutely, you absolutely can do checkpointing, and it's just like, you know, when do you checkpoint, and you know, those are some questions. And so this is really what we are doing, right? We're like doing a checkpointing, some kind of checkpointing scheme, just like with proof of stake. But yeah, I agree.
Can you talk a little bit more about the definition of finality? Like what exactly are you referring to? If you rewind one or two slides here, like what exactly do you mean by finality? Yeah, like here.
Yeah, so it just means that the history will never change. So in other words, like a block that is finalized is guaranteed on that fork to not ever be reverted.
Right, but
What kind of
there could still be a fork with a different opinion, right? I guess you're saying it could be a hard fork, but there could be no soft fork with a different opinion, right? It's kind of guaranteed by the consensus protocol. Is that the difference?
Yeah, essentially.
So it solves the UASF question. Yeah. Okay.
Yeah, I think it definitely solves the UASF question. Another solution would be to, you know, have a checkpointing scheme that you know, Phil mentioned.
Is the FFG also going to have a checkpointing scheme?
Well,
in addition to the FFG, so like for new nodes that are joining and don't necessarily know the full history of the protocol.
Yeah, so you definitely will need like information of like a block hash, for instance, of like the current validator set within some kind of time period to log into the network if you haven't been logged in before. So I'm going to dive into the FFG. So first, it's proof of stake layered on top of proof of work. So that means that there's going to be finality every 50 blocks, or an attempt at finality every 50 blocks, aka one epoch. It has some 51% attack resistance. This is, you know, I like the idea of hard forking away someone's coins. Although there are people who say, oh, well, hard forking away coins is, you know, hard forks are just too expensive for that to be practical. You know, that's once again a macroeconomics question. And clearly, and there's a reduction of energy waste from proof of work, which is great. So to become a validator, you just have some amount of ETH, you deposit in the smart contract. Now, the actual quantity of ETH, maybe it's like 1,000 ETH that's kind of been thrown around, but we have someone on the call and, you know, a bunch of other people working on this question of like, how do we, what are the actual like economic incentives that make sense for this protocol? And so the Casper incentive logic all lives in a smart contract. And this is just a smart contract that, you know, all the validators are aware of, and all the full nodes are aware of. So why do we use deposits? And this is this kind of like, there's often this cultural conflict between just like rewarding good behavior and rewarding good behavior while also punishing bad behavior. Some people are like, oh, I really like proof of work because it like, you know, only gives rewards. There's no, you know, deposits. But in some ways, I think that there are kind of deposits because you submit a security deposit, AKA, you know, you're like ASIC or something, and then your penalty would be mining a fork that doesn't actually get used, right? So I think that there are, even though it kind of seems like you should only reward, I think it makes sense to kind of do both. And the reason why we want to do this in Casper is we want to design a mechanism that really like restricts what the validators can do. We don't want them to be able to be like all powerful. We want them to be kind of serving the clients. And we also want to, you know, punish them really hard if they do something wrong. Like that is, hit them with everything we got in term, if they revert or if they cause a safety failure. And I went with the bucket thing again, just because people enjoyed the bucket when I did it last time. Cool. So this is the kind of, this is where the Casper FFG diverged from the previous Casper, where we now actually have just a single message type called vote. And so I'm just going to kind of go over that, and I'll bring some similarities between the prepare, commit, and the vote thing later. So chain is chunked into 50 block segments called epochs. Every 50th block is a checkpoint, and finality is achieved when 2 consecutive checkpoints receive 2/3 votes. Great. So we have these validators. They submit some votes to the miners get the votes, and they submit them to the block, to the blockchain, right? And they mine blocks that include those votes, I should say. So now this checkpoint has been justified. So this is, you know, when it's yellow, it's justified. And there is, each one of these votes, by the way, is not only referencing this checkpoint, but it's also referencing some checkpoint in the history. I just didn't actually show that checkpoint. And so, right, they have these votes, and we do this again, right? So this is one epoch, and the validators submit some votes, and these votes take the form validator index, target hash, target epoch, source epoch. So basically, we've got, this is the target checkpoint. This is the source checkpoint, and the validator index, pretty straightforward. You know, this is maybe the first validator or something. The target hash, just the block hash of this block. The target epoch, which is just this epoch number, and it's also called the target height in the paper. This is, you know, you can call it what you want. And here is a important piece of information. So in the last protocol, we actually had a slashing condition for preparing on top of a checkpoint that did not, or referencing a source checkpoint that is does not have 2/3 votes, or prepares actually at the time. Now we've actually replaced that slashing condition with just a like state transition constraint. So in other words, if you submit a vote, it won't actually go through to the blockchain unless the source is already justified, aka has 2/3 votes. So that means that as the if I were a validator and I submit a vote and I'm referencing something that maybe has one third votes, it's just going to say like, oh, it's going to assert false, basically. And so this is how we build up the chain, right? We get this like justification, and then we reference it, and we build these supermajority links, is what they're called. Okay, so we have this vote, great, and the miner mines the block, and we've got a justified checkpoint here with 3/4, and we now have a finalized checkpoint. So this is justified. This is our supermajority link between this source and the target. Which is constructed with all those votes, and we have 2 in a row, which means we now have a finalized checkpoint. So this is actually very similar to kind of the prepare and commit, right? This is kind of well, I'll actually go into kind of how it relates there soon. But before I do that, any questions on this? Great, I guess it's pretty straightforward. Casper FFG is like super nice. So why do we need 2 in a row? This is like, sometimes it's kind of confusing, and hopefully this is a relatively good intuition for why we need 2 in a row. So essentially, to be finalized, for a block to be finalized, we need to know that everyone else knows that the block is included in the main chain. So to actually know not only that everyone said that this block is included in the main chain, but to actually know that everyone else knows that everyone else said this block is in the main chain. So for that, you need 2 rounds, right? You need 1 round to announce the block that you believe is in the main chain, and receive 2/3 messages of that type. And then you also need to announce that you've heard that 2/3 of the validators have sent those announcements, and receive those same messages from 2/3 of validators. So you're saying like, I think this block is in the main chain. Everyone says, I think this block is in the main chain. And then everyone says, okay, I actually heard everyone else say that this block is in the main chain. And so that's how you actually know, like, okay, I know that this block will never change because I know that everyone else knows that it's in the main chain. It's like one of these like common knowledge thingies. Well, it's similar, I don't know.
Carl, can you talk a little bit about where the number 2/3 comes from? I mean, I know it's like a Byzantine fault tolerance thing, but it'd be good to understand that.
Sure. So this is something that always comes up, and I'm actually it seems to be just a reasonable threshold for kind of having like 2 faults. So essentially, you can make it doesn't have to be 2/3. Like it's this common misconception that it has to be 2/3, but you can actually just reason about how many people would have to equivocate depending on what kind of threshold you choose, right? So if you require a like 50% or 51% consensus on before if your threshold is 51%, then what happens is if like 1% of the validators lie and they say, I believe in this checkpoint, oh, I believe in that checkpoint, then you can have 2 finalized checkpoints, just because, right, you have 49% people vote on one, 49% of people vote on the other, and then you have 1% voting on both. And so you only are able to punish 1% of the validators. So that's clearly like not what we want. And so this is where the kind of 2/3 comes in, because it's like a nice sweet spot where it's like you have 1/3 voting here, 1/3 voting here, and then you need like this maximum number of 1/3 that's going to be voting on both. And so we kind of get this. It's, I don't know, it's kind of a sweet spot. But that's a very good question, because that always comes up every single time. Does that make sense? Hopefully. So now, why 2 in a row? Well, we have this is kind of maybe if you've seen the prepare commit thing scheme, then you can actually think of each vote counting as a preparation for the target epoch and a commitment on the previous epoch. So basically what that means is it's like saying it's announcing that you believe this block is in the main chain, right? Like a preparation, that's what I'm calling it, for the target epoch. And then it's also an announcement that you've heard 2/3 of validators say, say that they believe the previous block is in the main chain. And when I say the previous epoch, this is like only for two in a row, right? I'm just kind of assuming that it's 2 in a row. So I'll kind of show what that means, right? When this validator submits their vote, they're saying, I believe this block is in the main chain, right? But because there's also this link to this previous source, the source epoch, that means that this validator also must have seen 2/3 votes on this block. And because this is kind of like enforced using the state transition thing that I was talking about earlier, it can actually serve this like dual purpose. So this is how we got rid of the like prepare and commit, and we just replaced it with one vote. But now our votes are kind of doing two things at the same time. And so it was a logical progression.
Sorry, can I ask why you have 3/4 instead of 2/3 there? Is that supposed to be the same, or are they?
Yeah, so maybe no, that's a very good question. Maybe by presentation is a little crappy. It's just because there's 4 validators, and I just assume that they all have the same weight. But yes, it is 2/3. Like that is the threshold that we need. It's just that this I don't know. I just had 4 validators.
Will likely be above 2/3.
Yeah, it'll likely be above 2/3. That's true.
Okay, thanks.
Yeah, I realize now that that's probably pretty confusing. Cool. Oh, actually, technically, when this vote gets submitted, it should be 4 out of 4. Anyway, cool. So now, like, on to slashing conditions. So burning the validator deposits if malicious behavior is detected, right? So once again, we're burning the deposits. And I actually got a question on this. So why do you burn deposits rather than redistribute them? And I think this is actually a pretty cool thingy. The reason why is if you were to redistribute the deposits to the other online validators after detecting some kind of slashing, then what that would be doing is that just lowers the cost of an attack, right? Because if you are both the validator that causes the safety failure and the validators that are online validating, then you just redistribute the money back to yourself. And actually burning is similar to redistributing the money equally to all Ether holders across the community, right? If you lower the supply, increases the value. I mean, not always, but so no double vote. This is our first slashing condition. This is kind of copied straight from the paper. Basically, it just means that 2 votes cannot have the same target height or target epoch. I've been using target epoch. In the paper, it uses target height. I apologize for confusing the terminology. It's just, I like using the word epoch sometimes. So pretty straightforward, right? You have this fork, there are 2 checkpoints, and you've got these two validators. They're kind of evil people. Everyone's submitting their votes, but then these validators submitted votes on both, for both chains. So boom, now we have 2 justified checkpoints. So this is not good. This is, 1 step away from having 2 finalized checkpoints, two conflicting finalized checkpoints. And that's basically, by the way, this is what the slashing conditions are for. The slashing conditions are solely there to prevent 2 chains from being two chains from being finalized without like any penalties. This is like solving the nothing at stake problem. So essentially what will happen is your other validators are going to notice that that this validator submitted two votes, submit evidence to the miner mines a block, which includes a reward for that validator for submitting the evidence. Right now it's a 4% finder's fee, and slashes the two validators on that chain. And so then the same thing happens for the other chain. Gets a reward, slashes the validators. right? So this is kind of how we fix the nothing at stake problem. Cool. So the second slashing condition, maybe slightly more complicated. I kind of simplified the diagram just because it requires so many blocks. No surround vote, right? So basically what this means is you can't have this structure where one vote is completely surrounded by another vote. And it kind of makes some sense intuitively, because this vote is ignoring the fact, this is, by the way, these are all votes from one validator, right? This evil validator. So this vote that is referencing this, target of, target height 5 and source height 2, or target epoch 5, source epoch 2, is not including this information in it. And you'll see that, like, okay, now I can if I were able to do this, I would just be able to like justify and finalize these blocks, and then have no penalties for kind of skipping over them, and that would pretty instantly cause a fork without any penalties, and two checkpoints to be finalized. So this is clearly not good, and this is actually the only other slashing condition. And so unfortunately, I'm not giving you an exhaustive proof of like why these two are sufficient. However, Yoichi, who is awesome, formally verified these rules again, and it turned out to be, number one, easier to formally verify than the previous one with like all the different slashing conditions, and I think it's significantly simpler. So you can actually check out his formal proof in Isabel. Boom, pow, PoS. I just want to make this joke again. I find it very funny. Yeah, great. So I guess any questions on the slashing conditions? You can let me know. So now the kind of resisting the proof of work attacks. Right, we've got these validators. They're submitting votes. This checkpoint got justified. This checkpoint was finalized. Submitting more votes. This checkpoint justified, finalized. And it's important to note that like once you finalize a single block, all the blocks in that history are finalized, which is why we can just like finalize every 50 blocks or whatever, and it's we can reduce the overhead significantly. And notice we're using the proof of work as the block proposal mechanism. That's kind of like a key term if you want to be designing these protocols. It's like you have your safety guarantees, and then you have your like block proposal mechanism and whatnot. So proof of work attack. Oh no, what's happening? We've got that Ethereum ASIC. Boom. They didn't change our fork because we finalized these things. Proof of work attack failed. Go Casper. So, ta-da! We solved that that UAS F problem. Hopefully, you're convinced that it's a problem. but yeah. So these are just a really quick overview of the like economic incentives, and why these validators are actually validating in the first place, right? So we've got these validators. They're in the like economic paper that has come out. There's this function. Basically, what it means is this is last finalized epoch, and this this is the current epoch. So we've got increasing finality time, increasing the time to finality lowers the utility of the blockchain, right? Oh, here's actually, I forgot to give a real reason why finality is so like important. It seems it seems maybe trivial if you're thinking of our current state of Ethereum, to have this like finality every 20 minutes kind of thing. But it's actually really important when it scales up. So if you have a blockchain that is like sharded, and you have plasma chains coming out of it, and you have all of these huge amount of economic like activity going on this chain, then it's super useful for protocol designers to know that every 20 minutes you can check to see whether or not you can trust the blockchain will be reverted or will not be reverted, right? Like there's this thing that you can say, okay, I've waited this period of time. I know, you know, the blockchain considers this final, and so it's not going to change. And so in my protocol, I can say, okay, once the block is finalized, now I'm able to submit like fraud proofs or something to disprove the fact that that should have happened, right? So you can put a lot of weight on this finalization, and you can also just query it in any of your smart contracts. So anyway, so the increasing finality time clearly is going to be hurting the blockchain, and where the justification for this kind of like log base 2 is that like the difference between 1 minute and 2 minutes is finality is not that great, but the difference between 1 minute and an hour finality is like, you know, quite significant. And so you know, it has a nice curve basically. So we've got these validators, they're getting paid on both forks. Then we're finalizing once again, but this time we did not actually submit enough votes to justify this checkpoint, and the validators get penalized. So notice that the validators who voted on this chain are getting penalized less than the validators who didn't. And you can kind of see, you know, I think I actually may have calculated the utility slightly wrong, but that's okay. And so you'll see once again, right, it's this asymmetric penalty thing. And so here, once again, we have penalties coming out, and they're even more significant because we've had to wait quite some time for a checkpoint to be finalized. And boom, yay, we finally you know, justified a checkpoint, and now we're paying people out. And we also can like pay out in relation to whether or not they actually contributed to that chain. So here's the cool thing about these asymmetric penalties is that if you have a fork, right? Let's say this is a network partition, right? And we have a period of maybe a month where both of these forks are not talking to each other, or it actually could be validator censorship or miner censorship. Then what will happen is, because these rewards are asymmetrical and favor the online validators, we will actually get to a point where both of those forks become finalized. And so there's, you know, there can be this like long dispute period, and then eventually conflicting checkpoints will be finalized without any slashing triggered, just by the very nature that these penalties have gone on for so long. And this is cool because if you think about a network partition that lasts for a month, and you imagine a reorg that like trying to combine those two forks is just going to be an absolute nightmare. And if we're like basing our economic system on these protocols, we need to be thinking about, you know, these kinds of things. And these things, like, people bring them up, and yeah, the solutions for that seem scary if you don't just have two forks. It's like how you have to do it, in my opinion. But
sorry, Karl, just to reiterate, you're saying that if the two forks evolve and go on for long enough and there's no finalization on either fork, then at some point the protocol just declares each fork is independently like validated. Is that, or finalized? Is that the idea?
yeah, basically. I mean, the idea is that you see these validators, these guys are online from in the perspective of this fork, and these validators are online from the perspective of this fork, right? And these validators are losing less money than these validators every epoch. And so remember, to finalize, we need 2/3 votes. And so as time goes on, the weight of the offline validators is getting less and less, and and at a more rapid rate than these guys. And so there's, you know, there can be a period of a month where both of these forks are actually completely finalized, just the very nature of the fact that these guys now have 2/3 of the stake.
Real quick, a follow-up question. You mentioned earlier that one of the chains would get penalized more. So in the case of a 50-50 split, how do you decide which one gets penalized more?
Great question. So this is on each one of the chains, the offline validators are getting penalized more than the online validators. So I tried to represent this with the number of negative circles, right? So these validators are getting, 2 negative circles, and these validators are getting 3. But on this chain, these validators are getting -3 circles, and these guys are getting -2. So that's how it's actually that both of the chains are, they're not aware of each other. They are just acting independently and eventually will kind of diverge.
Okay.
Cool.
But this, even if this happens, this still doesn't violate the finality thing, right? Because neither of those chains were finalized until the split happens, right?
Yeah. So essentially what will happen is you'll go on for a really long period of time with no finality. And this is something that is just going to be, I mean, that's super scary to begin with. But what will happen is you'll eventually get this finality, and they will be just completely separate forks. And so you'll have Ethereum, and you'll have Ethereum. You'll have like Ethereum fork A and Ethereum fork B, and you can trade coins from one or to the other.
And this touches upon liveness, obviously, which is what you're talking about, right? This is how we ensure liveness, as well as leaking, right? This is what's called leaking, right? Those validators that aren't voting, over time their weight goes down, and eventually we can like route around them, so to speak, right?
Exactly. This is, Casper is definitely a liveness favoring protocol, right? We want to make sure that this chain is going to keep on going, even in bad situations, because we want it to be super resilient.
Can I ask one more possibly dumb question about the finality thing?
Of course. I'm not dumb.
So we're saying here that, just to recap, right? Finality means that once a block has been finalized, that's it. It doesn't matter. There can't be any kind of soft forks or anything that sort of take away that finality. And so anyone looking at the chain can, rest assured that like that history is written and will never be rewritten. That's the idea of finality, right?
Yeah.
So what happens in a world where, maybe this is a different type of attack, but where the sort of nodes or validators or whomever sort of says that they've like upgraded the software, and that's because basically finality is guaranteed by the consensus protocol in the software. What if someone claims to be running, kind of the accepted version of Ethereum, but actually they're running like a malicious piece of software and could still kind of fork away and carry out some kind of 51% attack and revert finality because they haven't upgraded, right? That's not an issue in proof of work, but it could happen here.
So you're saying, from a client's perspective, they are not going to, if there's a client and they see, okay, I've received 2/3 votes 2 times, like in a row, and this checkpoint has been finalized, then their client is not going to accept a reversion, right? They'll receive whatever they want to receive, and they're going to say, oh, actually, no, I've already received a finalized checkpoint. I know what fork I'm on. Is that kind of what you're
Yeah, I think you answered my question. I was thinking from the perspective just of kind of miners or validators, but you're right. If you look at all nodes of the network,
Related follow-up. If you do have like, let's say 1/3 plus 1 dishonest, they could technically, let's say, permanently split the network into 2.
Yes.
Is that not bad? Because especially if you're doing like a I don't know what the numbers was, like a 12-minute epic or something like that. It seems like you'll be cycling through like a lot of different combinations of committees, and maybe eventually one of them, even if there's only some low probability that it'll be 1/3 plus 1 dishonest, that eventually does come up.
Yeah, that's actually a good point. So this gets into like the fact that we need to make sure that the economic incentive is always there for a committee size to be large enough. And it is true that it is like, I mean, it's terrifying to have 1/3 or to have 2 checkpoints that get finalized. But the kind of argument that I've heard at least Vitalik make, and I think it's pretty reasonable, is that if you do have some kind of condition where, let's say we're targeting 20% or 15% total ETH to be staked, or just a kind of random number, and these numbers are kind of in the works, then it makes sense to require client action if two checkpoint, if 1/3 of 20% of all ETH gets burned, right? This is like a cataclysmic event, and really should be avoided at all costs. And so if you go.
Yeah, I was going to say, but like, how do people decide, right? And isn't this just another example of the centralized ETH Foundation hard forking their way out of problem? I'm just
I know, that's awesome, dude. I'm so glad you're on this call. Because I needed more proof of work people. I was actually going to invite some other people, but anyway. So that is right. So it's proof of Vitalik. No.
You just set yourself up for it too nicely, actually.
I know, I did. It was great. I'm so glad. There's this attempt to take away the subjectivity of blockchains that has, I think, been detrimental. So essentially, there's this concept that proof of work is objective in some ways, right? You have this algorithm, and as long as you can compute, SHA-3, then you're set, and you can the longest chain, right? But there's always this like social consensus around what blockchain you're on and what you're using. So what is your actual proof of work algorithm, right? There's like a social consensus around that. It's not just like math from the heavens. So I think that being really afraid of letting the social consensus stuff play out is not really doing the kind of nature of these protocols justice, right? Basically what we want to do is we want to, in the normal cases, provide a really secure blockchain that, has all the disincentives we can possibly code in to prevent these kinds of cataclysmic events. But if there is a cataclysmic event where someone is really trying to mess things up, it makes sense, in my opinion, to let that be a social consensus thing, right? We can say, oh, well, there's kind of limits to what you can actually do with security deposits. There's limits what you can do with proof of work. There's limits what you can do with any protocol. And if it goes outside of our security bounds, we just let people decide. And basically that means listen to the ETH Foundation. No, of course not. Like, where
you gotta log into Twitter and decide from there.
Yeah, exactly. Log into Twitter. God.
Yeah, I mean, to provide the proof of work person counter argument, like,
yes,
there is the social consensus aspect in proof of work right now. I totally agree with you, and that's something like a lot of Bitcoin people kind of ignore. But there is, I think, something to be said for the idea of like trying to move away from that as much as possible, especially if you believe in this long-term, buzzwordy machine-to-machine economy type of thing. It starts to like beg the question of what social consensus could even mean in that context. Whereas I guess objectively deciding on a proof of work algorithm and just blindly sticking to it is pretty simple. But yeah, I mean, I don't necessarily disagree with either approach, and you definitely don't want to be burning energy. So
yeah, exactly. I think that's actually a really good point. Sorry.
I'm done POW trolling for this.
No, please keep doing it, because otherwise I'll be really like, incredible.
Well, and maybe slightly more subjective proof of stake chains are good at certain things, and more objective proof of work chains are better at other things. We shall see.
Totally. I mean, I would say I think proof of stake chains are superior in every way, but that's okay. No, I'm just kidding. I think that I think they're totally valid arguments on each side, and really what we're going to see is like the most concrete thing is that we are currently burning obscene amounts of energy, and I think we can do better. And so people who throw up their hands and say, "Oh, technology was created, and we can't do better," I think is just crazy. And I'm a fan.
I mean, yeah, I totally 100% agree. And like you said, there's even a bunch of proof of stake coins out there right now that aren't burning energy, right? And even though you may say their protocols are totally flawed and, people just haven't attacked them because they're not interesting or they're not big or they don't have enough money, like the same might eventually be claimable about Ethereum's proof of stake. Like,
yeah.
So yeah, it'll definitely work.
I think so. I think it'll work. I think that a lot of the arguments for or against are these like crazy macroeconomics questions that no one really knows the answer to. Oh, how costly is it to spin up an async farm? How costly is it to mine at a loss? Or how costly is it to hard fork when, IoT is running the blockchain? There's all these questions that are just too big for human brains. And we have to simulate it, AKA run it in real life.
Is there a target participation rate for FFG?
There is a body of work that is accumulating rather quickly for what that would be. John Choi, who's on the call, and of course, all the other researchers, but him in particular is working on kind of figuring out, okay, how do we get the participation just right? Balance the incentives.
Cool.
Is there like staked or delegated, like I don't know what to call it, but validation pools or something like that? Like can I leave my money in someone else's custody or trustlessly in someone else's custody and still validate? Or I think you get it. I think you get the question.
Yeah. So yes, absolutely. There are staking pools. We do not have a staking, Casper implementation staking pool, because that is, you can code any smart contract to do that. In fact, what you can do is something kind of silly, is you can have Casper staking pools where you run the Casper protocol to determine what the next vote should be for your pooled validator. So the staking pools are absolutely a thing, and that minimum amount of ETH that you need should be much less if you're going to pool it together. But it's just like a whole design area of how do we design the most trustless staking pool possible? And you can do crazy things where you create derivatives of the actual future returns on a staking pool, and trade those, or there's just like a million different things that you can do with smart contracts. And this is why crypto economics is so much fun. It's so wild.
And it is fundamentally different than like a proof of work staking pool or proof of work pool, in that your computers are not at risk if the pool acts nefariously, whereas the staking pool, there's definitely more at risk. So it's definitely a different decision on just linking up your computer to a mining pool.
Yeah, totally. You need to trust the staking pool's consensus algorithm.
So can I will I be able to put my ETH in a contract that I always know I can withdraw from, and somehow Casper, but somebody else will do the validation and voting, but Casper will know that staked ETH of mine belongs to that person?
Yep, absolutely. So you just code that into, a smart contract. You say, if any kind of smart contract you can write, you can do it. I send some amount of ETH to a smart contract. The smart contract keeps track of your balance. The smart contract waits for a certain period of time, submits a kind of bundled, logs in as a validator. You let someone else run the validation code for a period of time. You're accumulating money in proportion to how much you put in, and minus a little fee for whoever's doing the validating. And then after a 6-month period that was predetermined, the validator goes offline. You get your money back and your returns. Right. So something like that. That's like a super trustful validator. But you can then replace that validator, the person who's actually submitting the transactions for you. You can replace that with any kind of consensus protocol, with any kind of consensus logic. So you can, it's turtles all the way down. Cool. So really the little last piece is just kind of second order effects of doing these asymmetric penalties, where you essentially are able to, here everyone's happy. So we've got this possible, this is like the participation incentive for Casper, right? So we have these prospective validators and their expected return. Right now, it looks pretty good, right? The validators are making a bunch of money and everyone's happy. But if the chain continues and we get a fork, then the actual expected return, because we're like penalizing everybody, the expected return is going down, right? And which means that there are fewer and fewer validators that want to actually join. And so like what Phil was saying earlier is like, couldn't you have a small enough group that, causing a safety failure would be, not too expensive and isn't that scary? Well, yeah, this is like super scary. And this is why discouragement attacks are actually quite nefarious. Because if we, continue and we can say that like maybe these validators or these validators are intentionally offline. I should actually say these validators. So these validators are like intentionally voting on the wrong chain, which means that even though these validators are acting honestly, they're losing money. And all in the actual, like the general perception of like, oh, is Casper a good investment, is going way down. And so we have this problem where maybe now the prospective validators is, two dudes. And which means that the actual total deposited ETH is going way down, which then means that the attacker requires much less ETH to violate safety. So we have the same attacker, but a smaller bucket. Very sad. Ta-da. So the road ahead, some next steps. We've got we're moving to proof of stake, going to overlay it on proof of work. We get to waste less energy, pay less for security, resist centralization, arguably, and provide guarantees around finality. And that's, I think it's definitely important for applications building on the blockchain. And these traits are really critical for if we want to achieve Ethereum's vision of being the core blockchain that can scale out to almost to like a large extent. I'm not going to say it's the only blockchain, definitely not a blockchain maximalist, but there's I think that for us to hit the scale that we want to like be paying less, and we want to be burning less energy, and we want to have really good guarantees. And so some next steps, papers are constantly being iterated on, and actually in particular, I didn't update this recently, but in particular, like the economic incentives are a big push these days. And also the first full implementation of Casper is pretty much done, which is awesome. And a preliminary Casper Testnet, on its way. I call it testnet. And replacing proof of work completely is up next. And that's, that's like, Vlad has implementations of Casper that are, a different block proposal mechanism. Also, Phil has, Snow White, which is yet another block proposal mechanism. So I think that there are definitely ways that we can kind of move away from proof of work, but we want to make sure that they're like super, airtight before we do. And of course, we want to share the crypto economic techniques after all this Casper research. So basically, that's Casper. And thank you, everybody. I should have put better related resources, but
I have a question.
Sure.
Can you talk a little bit about how I, as a new client joining the network, how I would sign on and like get information about the most recent block, Finality's block, or some there's that point of subjectivity. Like, do we have any ideas on like the UI on that, or like how you come on board?
My best guess is you currently trust HTTPS and like the DNS record, DNS system for, receiving the right software. And so maybe you'll go on, Geth's website, Parity's website, and they'll have like hard-coded in an up-to-date validator set. Or you can go on Twitter and you can be like, oh, and it should be relatively easy to change, right? You could say, just like copy and paste a different block hash or whatever it is. And you can switch to that chain. So, if you're really paranoid, you say, oh, I know my friend is on this chain. Let me message him and he'll just send me his code, and I'll just copy that in, put it in my my client. So it's really, it is definitely one extra, I would say, maybe UI step, but I would almost argue that it was something that was there before because of that whole like proof of work subjectivity argument. But
right. And just to be clear, you don't receive any of your rewards until you actually withdraw.
yes, so the way that the withdrawals work, which I actually forgot to mention, was before you have to like log out, which means you like stop validating, but you don't get your money back yet. And that initiates this like period of time where it allows other validators to kind of submit evidence that you were misbehaving. Because essentially we don't want someone to equivocate onto two chains and then just leave. So you log out, wait a period of time, and then get your money back. Essentially.
Karl, I have a question about the discouragement attack kind of thing you mentioned a couple. Yeah. So what was the end of the story here? Like, how do we discourage or prevent this from happening? Because it sounds like a pretty crappy scenario.
Oh, discouragement attacks. That's a great question. So number one, we don't want them to be too severe. So essentially we want the penalties to be just right so that, you know, these things aren't super duper profitable or make it super duper easy to discourage all the validators. Like we don't want to be too draconian like regarding validators penalties, because that's a real way. The more we penalize validators, the more discouraged they're going to be. You know, surprise, surprise. Another way that we can discourage, and this is kind of your second layer solution, is you can say, oh well, if there's an attacker that's you know, clearly discouraging. Well, here's actually a fun kind of thought experiment that Vitalik came up with, where a attacker trustlessly commits to burning a certain amount of ETH as a validator. So they can like submit the smart contract that trustlessly burns ETH and you know, discourages other validators from joining. And that will in itself, before even any like actual network activity, that will already discourage prospective validators, because they'll know if I join, I'll get it. I have to join at a loss. And so you can then imagine, you know, the white knights of Ethereum for creating another smart contract which says, okay, you're going to burn this amount of ETH, well, I'll burn this amount of ETH, and you know, this kind of like stupid war goes on. So like they're like theoretically a lot of different solutions.
And then you bid up to sort of the marginal security you want to achieve and recreate proof of work.
Yeah, right. Exactly. So like clearly these scenarios are need a lot of exploration and are in some ways just kind of fun. But the more we can like explore the space of like possible actions that different people can take, the better, I would say.
So I got a question about the future of FFG. You mentioned like Vlad's block proposal mechanism. So I talked to him about it. I haven't fully gone through the details yet, but it seems like at least his argument is sort of like we have finality baked into the proposal layer. So eventually we'll want to get rid of.
We'll want to get what? Sorry, I think you cut off.
I think as you're saying, eventually in Vlad's future, he doesn't need the extra message to rally around finalized blocks. You kind of get it via the proposals themselves.
Oh, I see. Yeah. Oh, so actually, this is a great thing to bring up. So we have this like extra message, right? This like vote thing. But what you can actually do is, and Vitalik has even mentioned doing this, is taking those votes and just saying, okay, each vote is a block, right? And so you just like, now you have, that's like and so that's actually very similar to what Vlad is talking about doing. But if you do have every vote being a block, then I don't know.
Then you have a blockchain finalizing your blockchain, right?
Yeah, exactly. Blockception. And this is, I mean, I don't know, it's fun stuff for sure.
And that is essentially kind of implicitly what Vlad stuff is. Just to speak about Vlad stuff, there's some really, really exciting stuff going on there, but it's definitely still in the experimental phase, and the FFG stuff is like clearly a super solid way to move this chain over to proof of stake. So we shall see how the two bodies of research influence each other in the coming months and year. So. Yeah.
Vlad stuff is, and Vlad stuff has already really influenced the current Casper implementation, like the whole, slashing conditions, et cetera. Like this has been definitely a real iteration between Vlad and Vitalik, kind of going back and forth with their different protocols. And there's still more refinement that can be made on both sides. But I actually think, okay, I'm going to publicly say my theory is that the Vlad's and Vitalik's Casper, if you do votes as blocks, they're so close. I want to like prove that they're the same, but anyway. I think that would just be very satisfying to realize that we're all working on the same protocol.
Agreed.
And then we can define a class of protocols, maybe call them consensus protocols or something like that, all of these things are.
Wow. It's almost like we're starting in a field.
Rock on.
Great. So, I mean, I have one little like extra thingy that I'll do is just like, here's the Casper contract in its current form. And so like, if you're curious, most of the logic when you're actually implementing this thing is in this Casper contract. And so this is so funny. I didn't realize I was there. So the like if you wanted to deposit, right, you just send a transaction that calls this function. You give it your validation address. That's kind of an implementation detail, withdrawal address, and it logs you in. And there's like log out, right? That defines all the other stuff. So the cool thing about this is that most of the actual consensus logic is in a smart contract. And what that means is all of the nodes that are running the software don't have to re-implement the same consensus logic over and over again and like realize that there's inconsistencies. We can all just like implement it just once and security audit and kind of be done and formally verify it, and it just lowers the complexity overall significantly, right? And even here's submitting a vote, right? We just send a vote message, check to see that it's check the signature, like a bunch of different checks, and pay the rewards, basically process the rewards, right? Like these are and even something like commit or frac. Let's see, yeah. So even stuff like the actual number of votes on a particular chain is in the smart contract. So essentially what you can do is you just like, I am a node, I want to know how many votes are on this are on the chain that I'm looking at right now. I just query the Casper smart contract and I get it returns a decimal, which is the percentage that have voted. So these are like, it actually makes Casper super simple to implement. All you're doing is you have the smart contract, and then you have your fork choice rule. And your fork choice rule says, I'm going to look at I'm going to like run the smart contract and see what the smart contract tells me to do. And then I'll follow that plus proof of work.
And we'd have to fork the protocol to allow this contract to issue new Ether, correct?
Yes. So this is actually a great point. I'm glad that you brought it up. Is we can actually deploy the smart contract before Casper is even really a thing. And or before we can deploy the smart contract before we hard fork, and we can actually just run the validation process on the main chain and just like see how it goes. And as we're running it on the main chain, we can even do funky things like issue like token ETH that is, you know, redeemable at the hard fork. I don't know if we're actually going to do that, but like you could do funky things and just assume that it'll stay in sync. Something that I actually didn't bring up, which is a good thing to bring up, is like, okay, how do the validators know which checkpoint to build on? And the way that they know is like, if you have 2 forks and 2 possible checkpoints, then you just like wait a certain depth and you choose. Don't know how that came up, but anyway, important things that I remember to say. Yeah, so I mean that's basically that. I'll do a quick Docker compose up. We've got a you know, a validator, a miner, and a you know, bootstrap node all running. This is all going to be gibberish, but you know, you can pretend like things work, just like looking at the matrix. There's a lot of weird debugging things, but it's, you know, we have a miner and a validator all talking over a network, a simulated network, albeit, but it should be a real network soon enough. So that's some exciting stuff.
So I'm sure all of the viewers out there are going to want to know the answer to this question, and I'm sure that you don't. But when is this going to be on the main chain?
I have no idea. It will be ready when it's ready, all of you internet haters. Oh my God. Shout out to the internet haters, though.
When Casper IPO?
We have a pre sale coming up shortly.
Yeah, I'll post an address that you can send your ETH to later.
U.S. investors, good.
Yeah, we accept all. Just we forked my Ether wallet and wrote some insecure code to accept money. It's great stuff. Yeah, I don't know. I think that's mostly all. I don't know. Thank you all. If there's any last questions, feel free to ask, and otherwise,
I have one more question.
got it.
So there's presumably going to be a bunch of these like economic parameters about rewards, etc. Are any of these going to be dynamic, and are any of these going to be constants that maybe we might expect to fork in the future? Or do we kind of expect to have these to be constants that are just like really solid and good? And John Choi maybe knows these better than you. I don't know.
Yeah, oh, he totally does. And I'll let John Choi talk about the economic stuff, but I just want to definitely shout out to ETH, to their research, research.ch, ETH research. And this has like a bunch of different, you know, posts which talk about all these different like economic parameters. Right now they're just constants and we're going to mess with them. But John, do you want to actually talk about like the economic stuff, what the current state is?
Yeah, sure. I posted a bunch of stuff in the chat, so you can look at that. But just briefly on ETH research, I shared most of my recent research, starting with the participation constraint. So I think earlier someone had a question about participation. The way that we're thinking about it is we're taking like roughly like a fixed income approach, which means that we'll have some sort of target that says for this amount of risk, and risk defined by a standard deviation of the return profile of a validator. We might assume that, like, let's say, for example, you want to target a 15% yield for these validators on average per dollar. Then we might say for a target amount of X dollars of total deposits, the numerator should be X dollars. So we'll set that as a constant. And then over time, that yield will be larger when the total deposits are smaller. But if our hypothesis about the yield for a given game is correct, then more and more deposits will join the game until that yield is computed out, right? So you can kind of take a look at how we're modeling that in the various posts and let me know, and we can talk about that.
Cool. Is there any other fun economic stuff that is worth mentioning?
I mean, I know we're running out of time, but I think the rough overview is we have some implications around how do we connect the capital asset pricing model, which relates required return to risk and standard deviation. There's also a model around I guess, liquidation or liquidity-based asset pricing model, which kind of tackles the questions around how long should the withdrawal period be. I think there was a question around when do you actually get your yield. Depending on how liquid that is, that required return will go up higher. And if that return is higher, then there will have to be more issuance, which affects the price of Ether. So these are very important questions. Another one is a concept called ulterior factor analysis. That's supposed to be the, I guess, like the analogous idea to griefing factor analysis, which looks at what are the endogenous attack vectors within a proof of stake network or just any consensus networks. And what griefing factor does is it talks about we should really bound the amount of damage that an attacker can do within the protocol. So like if I have $100 deposited, I shouldn't be able to do more than, $200 or X number of dollars of damage to Karl's deposits. But what ulterior factor analysis is doing is it's really nodding to the fact that as an attacker, there's a lot of ways to get returns, and a lot of those returns are going to be seen outside of the protocol. So if you're coming from a competing protocol and say, hey, doing 10% damage to Ethereum's price actually will do direct benefit to my project, then you might be able to say, how do we quantify those things and limit the damage of that by targeting certain total deposit levels. So definitely check that out. And if you have any thoughts, feel free to leave some comments.
Awesome. Yeah. So we had so much economic stuff to do and so much fun. Should be the most exciting stuff. Cool. Well, thank you everyone for taking your time and also asking so many amazing questions, and I don't know, all the love.
Thanks, Karl.
Thanks, Karl.
Thanks, Karl.
Thanks, Karl.
Thanks.
I'm gonna save this chat.
So are you gonna post this or what?
Yeah.